Welcome to a SimCenter AimSim Student Edition tutorial covering machine dynamics and vibrations. The problem statement for this tutorial is the same as the past two parts of this series, with new goals being seeing how components from the mechanical, pneumatic, and signal libraries are all incorporated into a model, and understanding how to implement a control system into a model as well. This is part 3 of the series, which is how to add pneumatic pistons with a diameter of 70 millimeters that can offset the suspension's compression, and how to create a PID control system to maintain these pressures. Opening AimSim, the model has already been built upon from the one in previous videos, including the mass component and both of the spring and damper components. New additions from the pneumatic library begin with single pneumatic chambers with a single rod jack to replicate the piston, which are implemented for each of the suspensions. These components will work in parallel with each other on the mass with the linear node components. Port 1 for each of our pistons will be connected to an orifice, and then from there to one central pressure source, sending the total value to both pistons through a 3-port pneumatic junction. The last new addition is a gas definition component to impose the properties of the gas used within the system. Moving to submodel mode, Premier Submodel is acceptable. Looking at the parameters of the model, the values for the mass and spring and damper components are completed based off of previous videos and contain the global parameters shown. Each of the pneumatic jacks will have the same parameters, being an initial displacement of 0.025 meters, a piston diameter of 70 millimeters, a rod diameter of 10 millimeters, a length of stroke of 0.05 meters, and spring rate of 0. For this model, the piston must have an initial displacement for the mass to push down on and utilize the suspension if necessary. Making this initial length 0.025 makes the suspension's maximum compression 0.025, as that is when the piston is completely closed. Each orifice will keep the default parameters. For the gas definition, the fluid will be set to air, whose properties are semi-perfect. The pressure required from the pressure source still needs to be determined and can be calculated. The force from the pressure on the piston must be equal to the weight of the trailer, which is found to be 9,810 newtons. Next, the area of the piston must be calculated and can be determined to be approximately 0.003 meters squared. With the required force and area, the pressure can be found to be 25.49 bar. Because the pressure source in AimSim will send the same value to both pistons, the parameter value used will be divided in half, being 12.745 bar. Before entering this calculated value, one more variable must be taken into account. Opening the parameters of one of the pneumatic jacks, pressure within the rod chamber is pressure that will be acting against the pressure on the piston face. In order to compensate for this, add atmospheric pressure to the calculated value within the parameter window of the pressure source. An alternative method to solve this issue is to change the units for the pressure in the rod chamber and the pressure source from bar absolute to just bar. Now in simulation mode, make sure that linear analysis is enabled to be able to evaluate the vibrations of the system. For linearization times, add a time of 10 seconds, which will be when the model is stable, and now a simulation can be run. Looking at the mass displacement, the mass drops before the pressure is increased within the piston chamber to reach the desired value, making the displacement 0 once it is balanced out. Opening the eigenvalues window and changing the time to 10 seconds, the system has a new natural frequency and damping ratio when relying on the pistons. This can be attributed to a new stiffness within the pistons that varies from what is present within the suspension. Now that pistons have been confirmed to support the system, a control loop can be implemented rather than using a simple pressure source. The control loop will begin with constant sources for each side that will establish the goal value for the system. This goal will be compared to the actual value through a subtraction component, and the value being subtracted will be the compression of the suspension, sent to the subtraction component through a displacement sensor. The difference of the two is then pushed into a PID controller component who will take this value and modify it as an output signal. For this use case, the output signal will be in the form of a current which is sent into a control valve with 3 positions and 3 ports. The valve works where in position 1, the chamber of the piston will be connected to atmospheric conditions set at port 2 or T. At position 2, all connections are closed off, and in position 3, the valve is set to connect the chamber to a pressure source at port 1 or P. Each of these positions will be determined by the current the controller sends, making it so the system will operate where the valve increases the piston's pressure when the suspension is compressed, and closing the piston chamber off when that pressure value has been met, and with that, submodels can be assigned. In submodel mode, it is acceptable to use the Premier submodel action, but after doing so, notice the shape of what was the line connection between the orifice and control valve. Rather than being a direct connection, a pneumatic pipe is created with its own submodel and needed parameters. Once in parameter mode, the constant sources can be set to the desired goal for the suspension's compression, 0. Now looking at the parameters of the PID, a proportional, integral, and differential value are available. The proportional value is a number that will be multiplied by the error value. Now, opening the parameters of the valve, a rated current is displayed to be 40 milliamps, making 40 the maximum value the PID can send out, ignoring units as the port is in the form of a signal. A maximum error value will be 0.025, as that is when the piston is completely closed and leaving the mass only on the suspension. To have a maximum value of 40 from the product of 0.025 and a number, that number must be 1600 and will be the proportional gain value. The sign of this value must be evaluated as well, where a positive 40 milliamps moves the valve to the position 1, where the port for atmospheric conditions is opened. Negative 40 milliamps moves the valve to open the pressure source, which is the desired action at maximum error, meaning the proportional gain should be negative 1600. The integral gain is a value that allows for the error to become 0, which is not possible with the proportional gain alone, and through batch runs and tests is found to be negative 2000. A derivative gain will assist in damping oscillations when controlling the system, but are not necessary here. Remaining parameters for the new configuration include making sure both pressure sources are equal to what was established earlier in the video. Also, open the parameters of the pipes between each valve and orifice and decrease the length to 0.2 meters. And with the model fully parameterized, move to simulation mode. With the linear analysis option enabled, perform one simulation. Once finished, open the mass displacement plot to see a similar behavior as before, with the mass falling before being lifted back up by the pistons. Opening a plot for a suspension's compression and then that of a PID's output, one can see how, when the suspension is compressing, the PID is sending a voltage to allow pressure in, and after this compression decreases, the PID closes the valve to maintain this pressure. Opening the eigenvalues menu and moving to a time of 10 seconds, the system has 3 natural frequencies. The ones at 80 Hz are actually caused by the valves, who each have a resonance frequency that can be manipulated as a parameter, with the remaining eigenvalue being that of the system as a whole. And with the control loop completed, so is this demonstration. Thank you.